man.
Hope you're all doing well after what might have been a late night last night. Today we're going to talk about robotics and automation, and one of the favorite elements of automation that I've ever seen is the Krispy Kreme donut factory, if you will, inside Krispy Kreme donut shops. When I was in grad school here, about 10 years ago, Krispy Kreme opened up a few spots in the Boston area. I think now most of them have closed because they didn't quite have the demand for their donuts around here, but there was one up in Somerville, there was one over in the Prudential Center. So sadly, I don't think you can go and see this donut machine nearby, but has anyone seen it in person?
Doesn't every store?
I think most stores have them, yeah. I don't know if all of them do, but the two I saw have it. Huh?
They have a little production line in every store?
Yeah, a little production
They
line,
don't
yeah.
make them at a central place and ship them out?
I guess they just make, yeah, they just mix up the dough locally. So like that's kind of their claim to fame is, the donuts are really frequently fresh and hot, and then they turn on the sign when they're ready. So anyway, topic of today is robotics and automation. So that's a big topic, and I'll talk about some specific things, mainly how and why different kinds of industrial robots are used. But upon this slide, a lot of examples relevant to the theme. At some point, we saw the video of Tesla's factory, and now Tesla's automotive factory, while it still uses a lot of people and will for a long time, contains by number and I think by fraction of work the greatest number of robots and the most heavily automated machines in the world, and that improves their throughput and their quality. All the way down to, you hear the term robot being used for floor cleaning robots like the Roomba. Anyone have a Roomba vacuum at home? Do you like it? Does it work well? No, we got one and it just got confused. There's a lot of small rooms and it just kind of got lost and the cats got scared and came over. But seriously, like autonomous vehicles, right? There's a lot about self-driving cars, self-driving trucks, semi-autonomous vehicles these days, and if those of you who went to Amazon Robotics saw a great example of automation and robotics in the form of semi-autonomous vehicles to move material from place to place. And there are many companies that are creating those kinds of autonomous pallet carriers, pallet jacks to automate warehouse operations and make material handling more flexible, right? If you can do that, you don't necessarily need conveyors in your factory, which is a really big deal because the layout is more versatile, can be more flexible and changed more easily. There's a lot of really interesting research on humanoid robotics. That word means robots that can stand on two legs, or bipedal robots, and do things like enter unsafe areas like burning buildings or areas where there might be hazards such as an explosive device. This is a picture from the DARPA Robotics Challenge. DARPA is an agency of the federal government that funds a lot of really early stage wild academic and industrial research. And they had this challenge to roboticists around the world to build a robot that could complete a series of challenges, like hammering through a door, driving a pickup truck, getting into the pickup truck and driving it a short distance. And that advances the use of robotics and the balance and dexterity that's needed to perform those tasks. There's also a lot of specialized use of robotics, right? From things that you would say or will show, high volume production. These areas of specialized production, like winding composite fibers onto a complex mandrel for some kind of composite part or a ductwork or something for an aircraft. There's also some interesting work in use of robotics in construction. If you talk to architects who are thinking about how to make buildings more complex in their exterior design, or in fact automate the construction of buildings from houses to skyscrapers, a lot of people are thinking about robotics. This is actually a real example of a bricklaying robot. So it can pick bricks out of a stack and make a brick wall. And I think this is from a research lab in Zurich, Switzerland at the ETH, kind of like the MIT of Switzerland. And there's a great group working on that kind of stuff. And then this is actually an example of the Collier Memorial out by the Stata Center, the really cool granite structure. A lot of the granite pieces were machined in part robotically. So this is a big robot what we call a 7-axis robot, because it has 6 degrees of freedom on its arm, and then a 7th axis like a train track that lets it translate. And this is the keystone, meaning the center stone that basically holds the whole thing together mechanically, and the edges were cut robotically, and this lets you cut big heavy pieces of stone and do it quite accurately. So, and I think there was a lot of robotic grinding and polishing to make the curved surfaces. So in architecture and art, there's emerging use of robotics because of the ability to make big things and achieve complex 3D surfaces. And if you check out our architecture and urban planning department, Harvard School of Design, I spent some time at the University of Michigan and knew some people in architecture where they have an amazing fabrication shop and lots of robots that do stuff like cut foam and put bricks together and explore a lot of interesting concepts. So the overall view of automation is to think about how we can enhance performance of manufacturing processes using mechanical electronic devices that take the place of human labor. I left this question for you as the first one, but I think it's staring at you on the first page. And yeah, according to a textbook definition, a reading that I posted by Wilson, automation is defined as the automatically controlled operation of an apparatus, process, or system by mechanical or electronic devices that take the place of human labor. So herein is a very interesting question in manufacturing. How and why and when do we decide to replace human labor with a robotic or an automated tool? And that becomes the central question for a lot of manufacturers around the world nowadays, especially as the capabilities of robotics really grow in terms of what they can actually do. Robotics are inherently flexible in their capabilities because they can be programmed to do different jobs, but some of the things I'll tell you at the end really show they're becoming flexible. And also what we're seeing, though we won't really get into the detailed economics of this, is that the equation between labor, manual labor, human labor, and robotics is changing all around the world. And even in places like China, which traditionally have highly manual factories, I've mentioned before that Foxconn, one of the biggest manufacturers there, and others, is investing heavily in robotics. I think Foxconn is now the world's biggest user of robots. Foxconn is Apple's contract manufacturer, and that's really striking. So when we look at manufacturing systems overall, and Stan talked on Monday about what is a manufacturing system and how we break it down into the simplest element, we can think that in a factory, in a modern factory, automation happens at many levels, right? Machines can be automated, whether it's an injection molding machine with an automated load and unload, or a CNC machine that is automated in its tool path. You can also automate the material flow and handling through the factory. One example of material flow is robotic or automated ground vehicles, AGVs as they're called, like Amazon Robotics, or like the example I had on the first slide. You have robotic manipulation, which can sometimes fit into material flow and handling. It can other times fit into doing other operations like depositing adhesives or joining. Welding is a big application of robotics in the automotive industry. And then companies, engineers that specialize in automation of processes also have to think a lot about the controls architecture. Of course, the controls for the robot and how do you make the robot, for example, do its thing accurately and quickly. And we'll learn about how the characteristics of robots affect those performance attributes, as well as the supervision and optimization of the whole system. And you can imagine if you want to implement an automated factory, there's a lot of things you need to consider. The coordination of rates in the process. We saw that in the Krispy Kreme example, right? Whenever they designed that, it maybe was a bit less sophisticated than it is now, but they got to think about the manufacturing process for donuts, right? And how long and at what temperature the donuts need to sit in the vertical zigzag oven that lets the dough rise. And then, you saw the donuts moving at basically the same velocity through the system. So matching the sizes of the individual stations to make the donuts have the quality that's desired is important. Of course, the system needs to be robust against faults. You have to know what faults can happen and how things break down. Actually, my master's thesis here, I worked with Professor Alex Slocum, was about the design of precision interfaces called kinematic couplings for the bottoms of robots. So if you are running an auto factory, for example, and the auto body, all the metal parts are being welded together, if a robot fails, breaks, dies, and you need to repair it. The idea was that if you had a very precise interface between the robot and the floor, you could simply come in and pick the robot off and then put the new robot in as a replacement to minimize the amount of downtime. And I remember, this was 15 years ago, I remember the cost then that was expressed to us from Ford, who was our sponsor, is that it's $10,000 a minute downtime for an automotive body shop. That's because if you think of the total flow through the body shop, that was the value they were considering. So implementing those solutions is very valuable. We ended up working with ABB, which is a big robotics company to this day, and went over to Sweden, and the key data from my thesis was literally using a crane to pick a robot off the floor and put it back down, and pick it up and put it back down, and use an instrument to measure the position of the end of the robot, and then do the math to back into the accuracy of the mounting interface. Actually, some of the same methods I'll describe in a bit. So those are the kinds of things that we think about overall when it comes to automation. To give you a broad introduction, I'd like to show you another short video that I think is
rated at 60,000, 0.5 meters.
Sorry.
It started operation in February 2012. For this line, some
So we of course talked about how
for Crohn's as a single source vendor.
while they may be more expensive than we would like to pay, right?
Starts with a
Bottled water bottles, inexpensive.
comprising a Contiform
And here is
S30 with a Contifeed unit for the preforms.
The automation
A
for
preform interior
filling
cleaning feature.
Pellegrino water
and a
bottles.
pet view system for preform
60,000 an hour, is that what
monitoring.
they said?
The Contiform is
So
directly
1,000 a minute.
synchronized with a model fill VFS volumetric filler in a monoblock configuration.
This company has a lot of videos that show basically this kind of automation for beverage manufacturing, filling soda cans, filling beer cans, filling plastic bottles. At the beginning you saw the little preforms that are then blow molded into the bottles.
A CheckMax 713 FMHF then monitors the fill level using a high-frequency measurement. When they've been filled, the PET containers are passed through a container dryer, after which they arrive at the multi-module labeler, featuring 2 cold glue stations and a Canmatic unit for hot melt wraparound labeling. The 2 cold glue stations apply firstly a neckband and secondly a medallion, which is currently designed as a QR code for smartphones. The labelled containers are then passed to 2 end-of-the-line packers arranged in parallel, a VarioPack Pro FS for film-wrapped shrink packs, and a VarioPack Pro PFS for pads and film shrink wrapping. The layer pattern is then created by a RoboBox unit. A RoboGrip 4A loading robot assembles the stacks on the pallets. After which these are transported to a block-type warehouse.
Alright, so cool video. What are some of the things you noticed or that maybe struck you from what you saw? You haven't seen this kind of before.
Everything is about as fast as it can possibly be.
As fast as it can possibly be. Why couldn't it be faster?
Well, about approximately.
It's impressively fast.
It probably could be faster. I guess is they probably optimize with respect to cost.
Okay, yeah, so the statement is they may optimize speed with respect to cost. Maybe it's also about coordination. It could be, I haven't thought, super deeply about all the steps, that, one step is the rate limiting step, or there's like, handoff is very difficult between stations. I think, sorry, 1 second, on that point, like one thing that you have me thinking about is the filling process, right? If it takes a certain amount of time to fill a bottle, there's probably some greater difficulty if you fill it faster and faster. If you want to use a carousel filling system, right, there's the size effect, right? The time that's needed to fill the bottle determines the size of the carousel, and the diameter of that is probably going to be strongly related to the cost of the machine. So that might be one of the most interesting cost versus speed trade-offs. Yes?
I was gonna say the use of all these carousels are like interacting with each other, like
Yeah.
handing off. Between
Handing off, so yeah, so like having basically interlocking gears to do it that way. Anything else? What happened as you went through the factory? The rate? Well, the rate stayed the same in terms of bottles per time, but you see the rate gets slower as the bottles get grouped together. Of course, after they're all filled, then they can group them into pallets, and you saw different kinds of strategies for picking them up. Big robots designed to pick up relatively heavy masses, entire 24 packs of bottles, and do that robustly. I also saw a lot of real-time inspection. So looking to make sure the labels are probably on the bottles, or the fill level was appropriate, or another mode of inspection I believe is in the conveyors. When you saw the pallets being turned, there's probably a vision system, meaning cameras, that said, okay, I know that I need one pallet to be in this orientation over here, or one case to be in this orientation over here, and it would pick it up and put it in that place. And the ability to close the loop, if you will, between video and image taking and image processing and the control of robots has really been a big advance for use of robots in material handling like this. Because if the robot only has one specific program and has to find its thing in the same place and same orientation every time, it's a lot more difficult to automate a process. If you can have flexibility based on the robot finding what it needs to do in a particular, in a range of locations, then the capability of the process is much greater. So maybe that's a bit long of an introduction. Now I want to talk more about robotics, and the textbook defines an industrial robot as, let's see, an automatically controlled, reprogrammable, multi-purpose manipulator, programmable in 3 or more axes, which may be either fixed in place or mobile for use in industrial automation applications. Maybe a bit of a boring definition, but we see some interesting words. Programmable, we see 3 or more axes, that's just the way this is defined. We see in fixed in place or mobile for industrial automation. Yes?
So go back to that last
Yep.
video. I'm just curious, what sort of uptime would be typical for something like this? Maybe up for like 80% or like 99.9%?
I would say it's somewhere in between. I would guess it would be 95 to 99 or 99 plus. I think that that's of course a very important thing. I feel that they probably also have a trade-off between uptime and defect rate. So they can probably tolerate a certain number of defects and throw the defects away, or take those off and refill them, rather than try to either allow downtime when a defect happens, or try to work super hard to make the the defect rate 0. So I guess what I'm saying, maybe in the least clear way,